time-wise? Still 2 hours? Okay, so still half an hour or so. Yeah, should be fine. I was talking about the external used libraries. So we really avoid to reinvent the wheel, because there are a lot of people, or a lot of groups much bigger in size and specialized for those things. So this is a potpourri of what we are linking to in all parts of Elmer. So maybe pre-processing, post-processing, for instance, ParaView and VTK, but namely the number crunching part, which would be Trillionos MUMPS. And down to the right corner, the recent developments. So if you are working on an NVIDIA system, you can use AMGX. There is an interface in Elmer to offload the linear algebra to your GPU. Works also very nice. I have a gaming PC at home on a consumer grade machine. And Rock Collusion, this is currently our construction site, is important to run on the AMD GPUs, particular here at Cetonix, and back in my home base on Lumi. And maybe one thing for the engineering community. So we also have an interface to Salome. And also, I think we have an interface with OpenFOAM in Elmer. I'm not specialist on that side, but if you're using that kind of softwares, there is a link. You can let those softwares talk to each other. So Elmer and Salome, or Elmer and OpenFOAM. Okay, now we move over to numerics. Apologies for those who are not so intrigued by that part, but that's part of the game when you do finite elements. Talking of those, so we can have static or time-independent cases, transient cases, also time harmonic cases. Also doing scanning for eigenmodes. So there was a nice case where actually a glaciologist who is very fond of knives or swords got the eigenmodes of a big sword. I guess he made himself. He presented it at one of the glaciological sessions, so it was quite intriguing. So you can use that type of, let's call them time dependencies or non-dependencies. Discretizations, we have quite a variety of element families. So I have one colleague who is very, he comes from mathematics. There was a huge department at the Technical University in Espoo that really was specialists in finite elements. So Mika Malinen, he works a lot on that side. I think particularly I want to mention the P elements that in the more modern versions of the solvers are basically the standards we use. Element shapes, you name them all, two-dimensional, three-dimensionals, more or less you can think of. Yeah, and for the advection dominated equations, we of course have a residual-based stabilization scheme, but also we can use residual-free bubbles to stabilizations. And for continuity, we have mortar elements, so you can have interfaces that are of different meshes also moving. So that's particularly important in the electrical machines being used in Elmer. So non-conforming meshes. Linear solvers, yeah, mainly for the HPC system, the iterative Krylov space methods are of importance. We also have direct solvers for not too big problems working on HPC systems. That would be MUMPS, or if you're using MKL on Intel CPUs, that would be cPardiso. We also have some kind of adaptivity included in Elmer. So if you want to refine your solution, there are possibilities to do so. Right, and yeah, maybe I make a short break before we continue to the applications examples. Are there any questions online still or in the audience? No.
Just a quick just a quick question about this interaction with OpenFOAM.
Yes.
So you're talking about sort of transferring your case towards Elmer, or the two working together in a single solution?
Okay, I wasn't directly involved in that. I don't know how to reach you after that talk, but I can write it down and get the details. From what I know, as far as I know, is it would really the fluid part, because it was a big system and turbulent system. That's certainly not the chocolate side of Elmer, although we can do it. Was done in OpenFOAM, and I think it was more or less online linked to Elmer, where I think it was a fluid structure interaction problem, where the solid part was taken over. But details I cannot give you at this stage, but I can write it up and then answer if there is some forum to distribute the answer. One thing I wanted to mention, I think this comes tomorrow, but just to be sure, there is a web page. I think I show it actually in the end. There is a dedicated web page of Elmer, elmerfem.org, where you also have a link to a forum where you might even already find the answer. There's a search system, or if you don't find it, place the question, and it certainly will be answered because my colleague Peter Robak is basically permanently online. He sleeps from time to time, but generally these questions are answered in 24 hours. So if you have a particular question, I might refer you to that. I will show the link in the end of this talk. Okay, hereby I continue. So acoustics, not my field, but basically what we have is, well, I already linked it to Nokia. So this was some while ago when Nokia still was booming and wanted to miniaturize even more their microphones, for instance, or speakers. So we have the Helmholtz equation, linearized time harmonic Navier-Stokes. So even with the acceleration terms included, and also the thermal problems coupled to Navier-Stokes. And we can also do vibroacoustics. So this generally is then kind of also a fluid structure interaction. Another field, and that's actually where Elmer started from. So this is quite old stuff, as you might see from the reference down here. 2002 was the perfect crystal growth for the wafers, for instance, of which computer chips are made of silicon. It's called Solzhenitsyn growth. Sorry, the H is missing there. Of silicon crystals, which is an inherent multiphysical problem of fluid mechanics. Even magnetic steerers are used here, so electromagnetics, as well as of course thermodynamics. So you want to have a most uniform, perfectly mixed liquid phase, and then draw this perfect crystal from a seed out of it. And it was very important to keep constant environment parameters there. This was for a company called Augmatic that resided in Finland, and at this time of where this was studied was one of the leaders of growing perfect silicon crystals. So this one is again linked to acoustics, or no, sorry, not actually. Yeah, the lower right side or lower and upper right side. This is basically a microphone as it was used by Nokia. But I think the one that is animated is an accelerator, accelerator sensor made out of silicon. I think it was Weisele one of the Finnish companies that does sensors, and we simulated that. So this is basically also fluid structure interactions, because what you see in the coloring here is the pressure field induced by the movement of this sensor. Again, fluid structure interaction. So like, for instance, here on the right-hand side, there was a study done by my colleague Esko Järvinen, who has retired now, of a blood flow of an aorta that has a little bit of an aneurysm, to study how the blood flow evolves in there. So this is a really complicated fluid structure interaction problem. I think they used some artificial compressibility model there to get this solved. So because the artery is elastic body, and the fluid properties, I think they even used nonlinear fluid properties for blood. But don't beat me on that. I think there was a publication about that. I don't know, does this animate? No. Sorry for that, but I think we have anyhow enough animation. Okay, now I come to territory that I'm more familiar with. So that's one of the main academic science applications of Elmer. About around 2004-ish, we started doing that with my colleague Olivier Gagliardini from the University of Grenoble, Alpes Grenoble in France. He was in search of a three-dimensional open source Stokes solver, which we had at the time. Sorry, is there a question online? No. Okay. So there we basically started to go into computational glaciology, so the studying of ice bodies of any size. So we are doing glaciers up to ice sheets like here in the Greenland ice sheet, which, by the way, for the sea level rise is more important than the Antarctic ice sheet for that hemisphere, because the water always goes downwards. So northern hemisphere impacts southern hemisphere and vice versa. So actually, Australia should study the Greenland ice sheet, what's happening there. It's more important for you than the Antarctic ice sheet, on a little side note. But anyway, so what we are good in is solving the full so-called full Stokes equations, because ice sheet models apply reduced, so based on their shallowness, because ice sheets are usually 1,000 kilometers of long and only tops 3 kilometers thick. So it's basically a very, very shallow flow. And then you can apply on a large scale some asymptotic expansions with respect to this aspect ratio, and you end up with highly simplified systems that are basically solvable on a laptop nowadays. But if you do full Stokes, this is really a hard problem, and you need HPC. And in particular, it's important for these outlet glaciers, which basically contribute to the sea level rise. So if you look at Greenland, 99% of the ice sheet is really slow flowing ice. Okay, it's melting, hence by contributing, but the ice release is on very narrow channels, and there any approximation of the Stokes equation is not suitable. You need the full Stokes equation, and this is really hard to solve. And I dare to say, on that level, ice sheet side level, we for a long time were basically the monopoly on the planet to do that. Showing you how this works. This, for instance, is, on the right-hand side, we see the Western Alps. This was a study around the late glacial maximum, so about 20,000 years ago, how the ice or the glaciers grew out. So you have, for instance, the Black Forest here, Germany. Genève is somewhere here. Milano would be here. And you see how the glaciers grow over around the glacial maximum. This was a study connected to the high-level nuclear waste repository of Switzerland by NAGRA. They wanted to know how far the glaciers here, the Rhine lobe, extends and what conditions are under there, particular what comes to hydrology, because a glacier or an ice sheet heavily changes this, the groundwater flow underneath, and what you don't want to have is the groundwater flow directed directly into your repository, which is digged in somewhere there. On the left-hand side, you see hopefully an animation of a marine ice sheet instability. That's what's concerning people in the community, because they could lead to a rapid increase of sea level rise. This is the Pine Island Glacier, which was disturbed a little bit with melting at the front. And then you see the retreat in between a few decades, actually. Hopefully this works. Yes, now the perturbation is applied and tack, it goes. So this is a real concern. It's called MISI, marine ice sheet instability, and we might see those things happening in the Antarctic ice sheet particular. So the Antarctic ice sheet is basically very safe from above. Actually, a warmer climate will lead to more precipitation, and it's still so cold that it will be in terms of snow. So the accumulation on top will be actually increasing, but the problem is the warm water intrusions from the warming oceans and the changing weather patterns. In particular, in the Amundsen Sea sector, where Pine Island is, we have a situation where the warm water eats up the ice from below. And if you eat up the ice from below, exactly that thing can happen to certain glaciers that are based on a retrograde slope. And that's one of the main focuses I have with my colleagues from here, from UTAS in Tasmania. We are investigating that kind of systems in order to improve the predictions of sea level rise, because we are talking what I would think of the range of 1 meter sea level rise until the end of the century. And it causes a lot of problems for a lot of coastal areas all over the planet, particularly in those regions that cannot afford protection. Okay, continuing here, I hope I'm not going too much into details of that, but that's basically the field I'm working in. So meshing is always a bottleneck, not just in those applications, but particular because Antarctica is quite large. So you have to build large meshes and then refine them. And that's usually a serial process. So we make a trick. So basically what we are working on are flat, so two-dimensional domains, just the footprint, then making the refinements. And since the ice is very shallow, what we do is we read that footprint, the two-dimensional mesh, into Elmer, and then even in a parallel way, so it's already partitioned. And for each partition, make an extrusion based on some data input files that describe the geometry of the ice sheet and the bedrock, and then extrude them vertically. And this is a process that then can be parallelized and enables us to make these meshes of several million of nodes and elements. This work directly feeds, or actually indirectly, feeds into the IPCC, so the UN panel for climate change assessment. And we have been contributing with several of publications, also particular with our colleagues from UTAS to that body and to the assessment reports. I don't go into details. Connected to Elmer ice, there are several additional models, like for instance, a calving model based on a discrete element model, which is also developed at CSC by my colleague Jan Oström. So we can combine the continuum model and the calving model. Here, for the case I already showed you, we of course can connect to climate models. We need the climate input to get the precipitation and the melt, the runoff. For the marine ice sheet instability, and I hope this works sincerely. Yes, it does. This is also work with our Tasmanian colleagues. We have the combination of an ocean model in this case ROMS, which also is heavily supported by the Australian and also developed by the Australian community, and Elmer to get the interaction between the warming ocean, the melt rates underneath the shelf, and the ice dynamics that is a consequence of that. So this is really top-notch stuff. We also have a groundwater and permafrost model that might answer your question. So there is porosity and the interaction of ice melting with it, and also work together with Matt King at the University of Tasmania. We have a viscoelastic model of the Earth. So here you see a deformation, or you don't see anything. How disappointing. Okay, anyways, if you would have seen it, there would be a deflection of the Earth due to an ice load, and then the rebound after removing it. Going back to the porous flow. So for the Finnish high-grade nuclear waste repository, which is actually the only existing and soon operative on the planet. It's in Olkiluoto. We had to make a long-term safe assessment with respect to groundwater flow influenced by permafrost. So we are very far up north. So this is more than 60 degrees north, which is basically at the same latitude as the south tip of Greenland. So there has been a huge ice sheet and also permafrost during the cold periods. And by orbital parameters, there will be cold periods coming up in 50,000 years and about 100,000 years. And the task was to investigate whether those cold conditions can bring the permafrost to a level where the repository is, which is in about 400 to 500 meters underneath the ground here. Because permafrost really locally can change the flow. And for that purpose, we had a model that was based on very, very detailed measurements of the geology. As you can see here, the faults and everything included. So we exactly knew the parameter of porosity there. And we were making a model that was based on 5.5 million nodes run on the supercomputer. And we had to, and this was the challenge here, integrate for 120,000 years. This was very demanding. And the model is built up such that we have different models for heat transfer with phase change, of course. So you have to be able to change the water into ice, aka permafrost, groundwater transport, solute transport. So salts are very important because they highly alter the melting point of the pore water. And bedrock deformation, not by the ice overload, but by the porous pressure. So you change your porosity, your effective porosity, by the pressure or the permafrost you are producing inside. All is coupled together. So this is a very nice example of the multiphysics applications of Elmer. And we haven't done yet, but we could even combine that with an ice sheet, because I already said that an ice sheet is a very heavy load and it can tremendously change the flow of water underneath. The whole thing was done for Pawsey, which is the Finnish company for spent nuclear fuel disposal. And the results are, you can see nicely here, the curves of the temperature. So 0 would be here. So if 0 hits the 400-meter mark, it would be in problem. It doesn't. One thing you can nicely see in the beginning, you can see the heat signature of the spent fuel that was, of course, included. So the spent fuel is quite a heat source, and you can nicely see that, but it vanishes after quite some 10,000 years. But in the very beginning, you can see nicely the heat signature of the spent fuel. So the good news is there is no permafrost in a realistic climate scenario, because in particular, the first new ice ages, 50,000 years, is called off due to human activity, too much carbon dioxide in the atmosphere, there will be no permafrost reaching the repository. Then for the electromagnetics, as said, we have a ongoing cooperation with quite a few companies that are based in Finland, ABB, Kone Grains, Sulzer, yeah, you name them. So there is a cluster of that using Elmer and now also, I guess, on Lumi, if I understand correctly, to investigate and optimize their rotating electric motors. That's it for this part. I don't know if we can go to the next part or to discuss a little bit. We can keep the next part for tomorrow. Just to give you some concluding remarks. So Elmer is a genuine multiphysics code. It's a very, how should I say? I don't like the word legacy because it's constantly developed. So we started out with a Fortran version that is really far away from current Fortran standards, which we use. So it's currently, or it's permanently developing. You can follow that on GitHub. So it is based in the past, but it's permanently modernized like we do now for GPUs, but it has been around for some while. But we try to keep consistency between versions. So generally our models are backwards compatible. So it's a multiphysics code. You can see it as some kind of a open source poor man's version of COMSOL. Generally, we cooperate a lot with academia and also industry, mainly in Finland, of course. But that drives our development. So we don't go and say, let's do that. So basically, we get our impulses from projects. For science, I think it's a very good tool because my belief is that science should use open source codes and open source codes only. So science with proprietary codes is not really reproducible. Science with open source codes, you can always make a Zenodo repository of the very version of the code you were using. And then everyone can then go back and try themselves to run that setups. And that's the way it should be. And actually, that's the way it's demanded by a lot of, at least the journals I am contributing to. And I think it's good. Again, we don't put a lot of emphasis on the user experience. I'm very sorry for that. It's an academic code. So if you expect a perfectly working graphical user interface, you will be very disappointed with Elmer. If you expect something that doesn't demand a lot of, or actually zero, because it's open source, license fees, you're very welcome to use Elmer. I think that's one of the main assets of Elmer, plus that we do a lot of development on HPC systems, simply because we are also in the position to do that. We are a data center, as I mentioned before. Yeah, and I think that's about it. Are there any questions recently?